I come because I like to learn about what is going on in the industry. I like to hear from the contractors, especially because, being an engineer, sometimes it's good to learn from the contractors what innovations they're coming up with, and obviously to meet with other folks and see what, they're working on.
This conference is probably the most important event during the calendar year, so you cannot miss it. Because here you can meet a lot of people, contractor, supplier, competitors. So as I said, it's the most important event in the calendar for foundation business, and it's too important to don't be here, let's say.
We come because we get a lot of exposure to people who use our equipment. Camaraderie, a lot of camaraderie. Even with our competitors, we come out and we rub shoulders. Everybody knows everybody. It's just one big happy family.
Well, it depends on whether or not you want to continue learning. If you got a desire to continue to learn, then you need to be at DFI.
The good thing about this conference, you can meet a lot of people over and over, so you can make a very good connection with the industrial people.
Networking's huge. There's so many people here, just from different parts of the country and the state and the world even, and just seeing what processes they're using and their design methods and their equipment, and just really a lot of exposure, and also getting connected with those people for potentially future work, future jobs.
Come join us. If you're interested in anything in this industry, this is the place to be. This is it.
Hello everyone. Good morning, good afternoon, and good evening, depending upon whichever part of the world you are. Welcome to DFI India Groundwork 2022 Webinar 3. Recording of this webinar is prohibited. Online webinar recording will be available on DFI of India YouTube channel in approximately 2 weeks. And you can ask your questions anytime during the presentation using your Ask Your Question box beside the live stream. And now I invite our session moderator, Professor Subhadeep Banerjee, professor from IIT Madras, India, and executive committee member of DFI India. Professor Banerjee received his PhD in civil engineering from National University of Singapore in 2010. And at IIT Madras, he has formed 3 research groups to study the cyclic characterization of various types of natural soils, improved ground, landfills, etc., development of consecutive models of soils emphasizing their performance under seismic loading, and the application of fundamentals of dynamics to various complex soil structure problems. Professor Subhadeep Banerjee, we heartily welcome you to moderate the session. Over to you, sir.
Thank you. Thank you, Ashrita. Thanks, DFI, for inviting me to moderate this very interesting session of Groundwork 2022. I'm very happy to note that we have registration from across the globe, over 23 countries. So welcome all. It's in different time zones. So it's somewhere it's good morning, somewhere it's good evening. So now these are the sequences or today's agenda. So we'll have Mr. Seth Martin, who will discuss foundation and design of tall towers in urban environments. And after the presentation, we'll have an interesting Q&A session. Then we'll have the closing remarks and then the details of the upcoming programs. So now to introduce today's speaker, Mr. Seth Martin, Senior Project Manager at Langan. Mr. Seth is based out of Langan's New York City office, where he works on a variety of local and international projects. He received his bachelor's and master's from Virginia Tech. He specializes in geotechnical engineering design, instrumentation and monitoring, and construction oversight of various foundation types and support excavation systems. Seth collaborates with the developers and contractors to deliver innovative and practical solutions to complex excavation support and foundation designs. He has developed a strong background in soil structure interaction, excavation support design, deep foundation design through his work on Supertall and megatall towers in Manhattan, Malaysia, Saudi Arabia, India, London, Thailand, and UAE. So the title of today's lecture is Foundation Design for Tall Towers in Urban Environments. So without much delay, I hand over the session to Mr. Martin. Mr. Martin, it's all yours now.
Thank you, Professor. Thank you. And thank you to DFI India for having me this morning. It's a big honor. So again, yeah, the title of the talk is Foundation Design for Tall Towers in Urban Environments. So we're going to look today at two subject towers. One is the Kuala Lumpur Tower M in Malaysia, and the other is one Vanderbilt here in New York City. Okay, so first we'll start with Kuala Lumpur Tower M. And we have a lot to cover, so we'll go through these somewhat quickly. If there's any questions, feel free to leave those in the chat as we go, and we'll get to those at the end. So overall site location, we're in Malaysia to start. So this is in an area.
So Mr. Martin, you'll share the screen first?
Thank you for stopping me.
Sorry.
No, it's fine. I thought it was up. Let me know if you can see that now.
Okay, it's perfect.
Okay. All right, let's start over. Sorry about that. So again, looking at the two towers, so we have Kuala Lumpur Tower M in Malaysia and one Vanderbilt here in New York City. So Kuala Lumpur Tower M, we'll go to first. So this is in Malaysia. Looking down at the overall site as it is today, so this is in the KL Central Park. At the end of the park, we have the Petronas Twin Towers, which many of you are, I'm sure, familiar with. So this location is at the other end of the park. So we're facing the Petronas Twin Towers. One of the big challenges with this site is there's a new Malaysian Rapid Transit system that will be in place. This is this yellow line running up and down on the screen that will be in place when this tower is constructed. So that was a big challenge from an overall site constraints perspective. And we'll get into some of the other challenges with the overall ground conditions. So the proposed development, just to go through some of the metrics of the tower itself, it's a 700-meter tall tower, about 150 stories. Total weight of the tower is 9,000 meganewtons. Each of the individual mega columns around the perimeter will each have 400 meganewtons. So the scale of this is pretty incredible. And then the system is a piled raft. We have a 70-meter square, 5-meter thick reinforced concrete raft over a field of 137 2.5-meter diameter board piles, ranging anywhere from 60 to 105 meters below the bottom of the raft, and up to about 125 meters, 130 meters in some cases, below existing site grades. So some of the deepest piles in the world. And the current status is the tower is not constructed. The foundations are all in. The basements are all excavated. And at this point, there is a pretty long horizon for constructing the tower itself. So looking at the relationship with this Malaysian Rapid Transit station. So this is a cross section through the site, looking at the tower here on the left, and then the Malaysian Rapid Transit station on the right. So you can see here that the piled raft system itself is going to sit about 15 meters above the lowest level of the MRT station. And over here, we have 2 track levels, and we'll get into some of the criteria there. So overall, the MRT had very specific criteria that we had to meet. So we're putting in this massive tower, massive foundation system, and we have to look at how that's going to affect the tracks and the overall structure itself. So we had settlement criterias, angular distortion criterias here listed on the right-hand side. We were looking at the overall surcharge and bending moments and shear forces in the diaphragm wall here. And then we also had to look at how the groundwater levels at the site would affect the overall performance of the structure. So a big first piece for our approach to a project like this is the site characterization. So we know from previous work at the site and published work with the Petronas Twin Towers that this is a very challenging geological condition. There is a karstic limestone that underlays the site, and this limestone is essentially water soluble. So it's going to have various erratic profiles and cavities, rock pinnacles. We've seen towers at other sites where there's rock drop-offs as much as 50 meters within a single tower footprint. So very challenging conditions. So that's going to require a robust upfront site characterization. So just again, some kind of metrics of the overall site characterization here. We had 5,000 meters of SPT drilling, pressure meters, obviously a wide range of lab testing, strength, compressibility, and index testing. And the way we approach this project is to have a couple of different phases of investigation. So we didn't want to space out all the borings on a typical grid. We did an initial round of borings and then sort of focused in on more problematic areas. And then we followed up with the construction phase investigation as well, where we actually drill a boring at every single pile location. And this is to address this karstic environment and really understand at each different pile location, what is the expected depth to rock? Are there any cavities, any unusual conditions to identify? So this is a plan showing the overall initial two-phase approach to the design phase investigation. Through that investigation, we identified this weathered limestone layer, or what we thought was a weathered limestone layer, across the tower footprint. And the key here is we then proceeded with the analysis, proceeded with the design, and ultimately got into a construction phase investigation. So here we're showing the overall pile layout, and these were the estimated weathered rock thicknesses from the design phase borings. So we could see weathered rock thicknesses anywhere from 2 meters up to say 10 meters across the tower footprint. So a very thick weathered rock layer was estimated based on the original investigation. Through the construction phase investigation, two pieces there. One, this was a different contractor, and two, it was a generally just a better quality investigation. So what we found through doing these proof drilling points at every pile location was that the weathered rock was actually very sporadic, and it was not a consistent profile across the tower footprint. And so the key there is that this is going to obviously affect the overall tower performance. So that had to be evaluated prior to drilling of all of the production piles. Overall, it was a savings in the scale of the drilling. So here we're showing the estimated pile lengths based on the proof drilling versus the original estimated design pile lengths from the original investigation. So any of the negative numbers indicate a reduction in the overall pile length. So here we saw rock was a little bit shallower, quite a bit shallower, up to say 18 meters, 20 meters shallower. And here rock was a little bit deeper. So again, this warranted additional analysis, but overall this was very beneficial to really fine-tuning the production pile drilling quantities. And the overall takeaways, just to put numbers to it, so we ended up with 400 meters less of pile drilling from what was originally estimated based on the design phase investigation. Another big takeaway was this weathered rock zone was essentially non-existent except for some very local areas, and that resulted in a softer raft response, which was again very, very important to evaluate prior to construction. So that we did observe additional settlement in our analysis, and that put an increased demand on the raft. So this had to all be accounted for just ahead of the production piling. Thankfully, the settlement criteria at the MRT was still within tolerance. So we'll get in now to how we evaluated the tower's foundation performance and what our overall approach there was. So here's a snapshot of our Plaxis 3D model. So the tower was evaluated through Plaxis 3D through a wide variety of various parametric checks to see just how sensitive the overall performance was to the stiffness of the ground, the rock profile, and then also the pile length. The final approach here was to take all of the production piles to 2 meters above the rock. So we would essentially shadow the rock. The lesson learned on previous projects in this same park is going into the rock presents very serious problems. It significantly slows down the drilling, and you also start to run into issues with cavities in the rock, and you can have a lot of just a lot of construction issues that come out of that. So the overall goal was to see how close we needed to get the piles to rock to maintain a performance that was acceptable for both the tower itself and the adjacent MRT station. So the MRT station here is shown as well, and you can see here that we're modeling this. We're kind of peeled back some of the different elements of the structure to show the different levels. There's a single row of tension piles here below the MRT. So this is the overall model. And then just looking at kind of the two side by side, this diagram we looked at before, and then how that looks in the actual Plaxis model, and just the layering of the soils and the rock below. And then the overall performance. So here we're seeing up to about 95 millimeters of settlement. And this was kind of our best estimate of overall raft performance at the end of various analyses working with the structural engineer. And the big key item here is, okay, how is that settlement going to affect the adjacent MRT station? And what we looked at is both angular distortion across the tracks, angular distortion along the tracks longitudinally, and are those within tolerance. So we had a very strict criteria of an angular distortion of 1 on 2,000. So for a track that's 6 meters wide, we're allowed 3 millimeters of differential settlement across the tracks, which is obviously very tight. And then we also had an overall settlement criteria of 15 millimeters. So very, very tight tolerances, considering that we're seeing up to 95 millimeters of settlement below the tower, and we're restricted to as much as 15 millimeters of settlement at the structure that's immediately adjacent to us. So that goes back to just getting to a point where the piles had to essentially almost touch the rock to maintain these criterias. We're also looking at the overall pile load distribution and checking how that compares to obviously the individual piles capacity, both geotechnically and structurally. And then we're looking globally at how does the overall piled raft system's capacity compare with the tower's weight. So when we look at the combined piled raft capacity, both in bearing plus the individual piles, we're seeing a capacity of well over 50,000 meganewtons. So we essentially had a factor of safety of 5 on the overall foundation system geotechnically, and then the single pile geotechnical capacities, those were less. The factors of safety there are anywhere from about 1.5 to 2, so higher in some of the corner areas. So the key is that this is not a geotechnical capacity situation. This is a settlement issue, and so that's what we were really up against on the design side. Is, you know, how do you maintain these settlements to be within acceptable tolerances at the adjacent MRT station? And so then this is a couple of shots from construction. So here's the Bauer BG-72, which is the biggest drill rig that Bauer makes. And these again are to drill these 2.5 meter diameter piles, cast in place board piles, up to 130 meters, 125 meters below the existing site grades. So that's the overall story of KL Tower M. And the key there is that this is where we're going very deep into the earth to find the rock. Now we're going to transition to New York City, where rock is very close to the surface in most cases, and especially in Midtown Manhattan, where one Vanderbilt is, and just a very different approach. So we'll get into just kind of the opposite end of the spectrum here, with a tower that is going to sit directly on rock, and how do you deal with that, and just some of the different sort of challenges that we were up against at one Vanderbilt. So again, just where we're at in the world, we're now traveling to New York City. The real challenge here is there's a long history in New York City of various developments over time. We have a lot of very old infrastructure, both in adjacent subway tunnels, old landmarked historical buildings, such as Grand Central here, shown in this picture on the right. And then we also have critical utilities that run actually through the site. So what we're showing here in plan view is just an overall site layout. So we have the site here in red, and just south of the site, we have 2 subway lines that run below 42nd Street. And also, I should take a step back. For those of you who've not been to New York City, this is really the heart of the city. We're right next to one of the main railroad lines, main transit hubs, and then we have also very busy streets right here. So Madison Avenue runs right through the heart of New York City. Very busy street. There's traffic up and down the street all day, every day. There's pedestrian traffic all around this site. So how do you create this, you know, deep excavation to build the foundations for this large tower around and within all of this existing infrastructure and just the hustle and bustle of New York City? So again, we have the 2 subway lines to the south. We have the Metro North railroad tunnels, which run here along the northeast corner and actually encroach on the site. And then we have the Grand Central Station or terminal, which abuts the site immediately to the east. On top of that, we had a 100-year-old sewer line that ran here. This is the green line here that runs actually through the site. So that had to be removed and relocated prior to construction. And we also had some existing water lines that ran through the site to the south. So very different from KL in the sense that we're not trying to find, you know, rock. It's more, how do you deal with the existing infrastructure that's around you, and you know, keep that all protected as you excavate very hard rock and get into the ground there. So just a couple of pictures of what this looked like sort of mid-construction. So here we have Vanderbilt Avenue. This is looking east. So here's Grand Central Terminal, 100-plus-year-old terminal to the east there. And then we had 43rd Street to the north and 42nd Street to the south. We're at about the foundation subgrade. So this is about 50 feet below street level. So you can see all the various excavators doing some line drilling over here to get the rock out. And what you don't see here, so on the east side, behind this wall is active retail space. So we are right up against convenience stores and people shopping as we're chopping rock and excavating down below the footings that support that structure. At the south, we're right up against the subway terminal. So we have two different subway lines that run just on the other side of it. There's one bay of structural framing that you can sort of see here. Just beyond that are active subway tunnels that we're staying in service throughout our construction. And on the north-hand side, we have another active parking garage. So really, three sides of this site were fully functioning New York City, infrastructure and retail space. So very challenging there. And then what you don't see again below this mound of dirt is the Metro North Railroad that runs through the site. So that would ultimately be exposed and then incorporated into the project. Professor, can you see my screen okay? I'm getting a notice that...
Yeah, I can see, no problem.
Okay, so now if we look at the west-hand side of the site, again, 43rd Street and 42nd Street. Now on this side, we have Madison Avenue, which again, very busy street. This is the one side of the site that actually had real soil retention to handle here. So kind of a different set of challenges here, just really more, excavating up against existing structures and not so much dealing with the earth. Okay, so going through the proposed development here, this is actually a real photo. So as it stands today, One Vanderbilt is fully built. I understand it's essentially fully occupied, which is great for the overall project and the city. Another real photo from today. Okay, so the tower is a little shorter than Tower M. We're at 427 meters tall. So it's still a very tall tower. You can tell here that it's towering over all the existing buildings in Midtown. It will be is the second tallest office building in New York City, just behind the One World Trade Center. Construction was completed a couple of years ago. We have below grade connections to the New York City Transit subways, Metro North railroads, East Side Access, which is a new railroad line that runs below Grand Central, and then Grand Central itself. So we'll look at how all that interconnections look today. And then just some metrics on the overall materials that went into the tower. So 26,000 tons of structural steel, 4,200 cubic yards or cubic meters of concrete for the central mat foundation. We'll look at a couple of photos of that later. And then overall 43,000 cubic meters of concrete for the tower core itself. So this is an isometric view showing the final condition of the tower and all the below grade connections that are being created with this tower. So you have here one of the subway lines, and we're going to be connecting straight into that. So there's a pass through here. There's also a passageway connecting to other areas below grade. That'll provide some additional pedestrian flow there. And then we have connections into the Grand Central retail space. And what you don't see is there's another connection over here at the north into the lowest level, which is at the East Side Access mezzanine level. So that's about 50 feet below street level. So really just a huge improvement on the overall dynamics of this area of town and really just helping to create all this different interconnectedness between the various structures. So now if we look at the couple of cross sections through the site, this kind of helps you understand what we're up against. So if we look at this section A here on top, this is the cut north to south looking west. So here you can see we have these existing cellars, the existing buildings that were going to be demolished. And then we have this dashed red line, which is where we'll be digging to. So digging well below the existing foundations of the buildings that are demolished. And then we're going also about 20 feet below the adjacent subway structure that's thankfully sitting on rock. The good thing about this site is that we had very good rock, and we'll get into some of that in a minute. If we cut the section looking east to west, looking north, here we do have one area along Madison Avenue, again, where we're dealing with real earth pressures and earth retention below a very active city street. And then here you get a appreciation for, we have these two levels of Metro North Railroad tracks where we'll be excavating right up against their foundations. And how do you accommodate that? So again, our first step in the whole process is the site characterization. Here, the investigation was a little bit more straightforward because we are on rock. We're not dealing with very deep foundations here. So we had a series of test borings, and the key here was test pits. So we would actually excavate a small, say 1 meter by 1 meter, maybe 2 by 2 area to expose the perimeter foundations of some of these adjacent structures. We were advancing probes through the perimeter foundation walls to understand the relationship between our existing walls that were being removed and the adjacent structures walls, whether that was a subway tunnel or this Grand Central retail space here to the east, and just understanding the relationship there so that we could inform the contractors of the conditions and deal with how do you approach these very sensitive areas. We did do some more advanced geophysical borehole logging. So what we would essentially do is send a probe down the borehole, and this probe can map the in situ rock fractures and foliations. So here's a couple of photos of the rock core boxes, and you can see just from looking at this that the rock is generally very competent, sound bedrock. But we wanted to really evaluate, out of all these fractures, how much of these are mechanical breaks from the drilling, how much of this is in situ, and if it is an in situ fracture, what is its orientation with respect to the excavation face? And are there any areas where we're going to be dealing with potentials for rock sliding below some of these adjacent structures? The overall rock was extremely strong, as strong as concrete, if not a little stronger in some cases. So we were seeing compressive strength of the intact rock of 6,000 to 8,000 PSI. Typical concrete in New York City is around that same kind of range, say 5,000 to 8,000 PSI. And we had bearing capacities, recommended bearing capacities for the tower of 60 tons per square foot. And then the modulus we would measure as well through some of this testing to evaluate the overall expected settlement of the tower. So the geophysical borehole logging, this is a couple of snapshots of the results here. So the middle image is showing the rock as it is inside the borehole. So we can look at this and we can evaluate the orientation, the dip direction of the various fractures. So you can see here, this is a fracture that's relatively shallow, but it is a legitimate fracture. So we'll take those and we'll plot those in stereo nets, and we'll understand on each excavation face, are there areas where we may be worried about potential sliding? So we would evaluate that, and then that is a big piece of our overall excavation support approach. So getting into the tower foundations. So again, here, very different situation. We have shallow rock. So here we're not so worried about settlement, and we're not so worried about overall bearing capacity because we know the rock in New York City is very strong. Here, really, the challenge is holding the tower down. So we have a series of tied-on anchors. There was one kind of quadrant of the tower mat that was identified as an area needing uplift resistance or tension resistance. So that's this cluster of tied-on anchors here, and each one of these anchors can take 350,000 pounds. I don't know what the conversion is off the top of my head with that. It would be in meganewtons, but each of these anchors can take quite a large load. And so we would end up testing each of those. We'll get into that now. So just looking at what that looks like, we have this condition where you have a tall tower sitting on a shallow foundation, and there's a wind load that we're designing against. There's various wind tunnel studies done. And through that, we're coming up with a system of tie-down anchors to hold the side of the tower down that's wanting to overturn. So what we're checking here is a combination of the structural, there's various failure modes. So you have the structural capacity of the bar itself, and ensuring that that has adequate capacity. And then we're also looking at the geotechnical capacity of an individual anchor. So that's these arrows here, just confirming that this bond zone of this anchor has enough capacity that it can take the uplift force. But then the more critical piece, when you have these dense clusters of tie downs, is the overall global stability check. So what we see a lot in these situations is when you look at the cone, this theoretical cone of rock that's going to want to pull out of the ground, when you have a dense array of tie-down anchors, these various cones overlap, and you end up having less volume of rock and less strength of rock of the total cone than you do of the total force pulling up. So that's another big check that we do here to see if all these anchors are being pulled at once as the tower wants to tip. How does that? How do we confirm that the rock has enough global capacity that the rock wedge is not going to want to pull out of the ground? And so we'll see that actually control in these sorts of situations. And then getting into the overall construction phase of this. So we test each of these anchors. So here in the middle photo, this is a large hydraulic jack that's pulling on each of these anchors. We're testing these to confirm that their elongation is showing that there is an adequate free length, adequate bond length, and overall adequate capacity. So we want to make sure that the free length of the anchor is what it's supposed to be, and that the anchors, the load transfer zone of this anchor is deep enough in the ground. And here's a cool photo of the overall mat pour. So this is the central mat for the tower, and this was reported to be the largest continuous concrete pour in New York City in its history. Unfortunately, since then, there has been one other pour that we know of that's exceeded it, but at least at the time, it was the largest. So kind of a cool shot. You have the Grand Central Terminal in the background, and you can just imagine the logistical effort that went into getting roughly 400 concrete trucks into the heart of Manhattan. It was about a 24-hour period where these trucks were cycling in and out and getting this all constructed. So really a pretty amazing feat there, and just kind of gives you an appreciation of what we're up against in some of these very dense urban conditions with getting these towers built. So overall takeaways for us, again, the first phase of any tower foundation analysis and design is to characterize the site. But the key is to appreciate that the site characterization doesn't stop when your last boring is complete. Really, we're characterizing the site no matter what the foundation type is, even through construction. So whether that's proof drilling at deep piles or mapping the rock in the field, we have engineers on site who are looking at the rock and understanding if there's any areas where we need additional rock stabilization, any areas where maybe rock is more weathered than we expected, and really just appreciating that observational approach through construction. And then especially with Tower M, this advanced modeling really brought a lot of value to the project, and just being able to kind of fine tune the pile lengths and keep those piles out of the rock to avoid just all the various issues that go along with that, and being able to demonstrate that the tower performance and the MRT criteria are still satisfied without having to take those deep piles even deeper into rock. And with that, the deeper the foundations, the greater the unknowns. So even through construction, even with all this proof drilling, we still had piles where the rock depth didn't match the proof drilling. There were issues with choked trimmy pipes. There's just a lot that can happen as you get down further into the ground. So the key there is, we had some conservatism built into our models and into our estimated pile lengths to account for things that are going to come up in construction. There's always going to be issues, but there's going to be more and more issues the deeper that you're going into the ground, and just especially in these areas of the world where the ground is highly variable. Just making sure that you're not getting too aggressive with your design and cutting it too close, so that if you do have some issues with the pile coming up short or rock being deeper, things changing, that could have major impacts on the overall agency approval process. And then just with both projects, we approach these projects as a team, working with both, on our side as the designers, and then with the contractors and the agencies, and really just collaborating with these various entities, and understanding that these entities come from different, different values and different goals, but the common goal is to provide a safe and constructible design that ultimately is going to be going to get the job done. So that's kind of our approach to all these towers, and just working with various various entities throughout the process, and understanding that things are going to change and things are going to come up, but keeping the team dynamic and focus is critical. So that's what I have, Professor. I hope that was okay. Looks like I may be a little bit early, but I wanted to move quickly to save time for questions.
Yeah, I think it's fantastic, and it's pretty interesting. And we have, as expected, we have quite a number of questions here in the chat box. We start one by one. Well, first one says that was an analysis done to understand the effect of excavation close to existing MRTS on one side with relief of soil stress.
Yes. Yeah. So that's like a whole other presentation in itself. So we did a very advanced, a very detailed analysis with MRT, with their engineers, looking at. So the overall approach there is it's a top-down construction. So there's slabs that are built as we work our way down, and those slabs span from the common MRT KLCC Tower M diaphragm wall across the site to an opposite diaphragm wall. So yes, there's a very detailed construction sequence that we had to follow and model. And with all that, we were looking at the bending moments and shear and deflection in the wall itself, because again, this station is going to be built. The original intent was that it would be built concurrently with our site. Just the way that it all kind of worked out is that this structure is going to be built before we excavated. So it was a very detailed analysis for another more. It's probably a 2-hour presentation another day. Yeah.
Yeah, I think in the same line, the next question is, how did you overcome the excavation impact of the adjacent structure? I think what you just now described. I mean, it's a detailed analysis without MRTS and other thing. But there is another question towards the end. It will come. Like, what about the shoring system of this your Manhattan Tower? I mean, what type of shoring scheme you have used in this Vanderbilt Tower? Is there? Can you want to highlight that?
Sorry, I'm looking. Where is this question?
No, this question is come quite sometimes towards the end.
Okay.
Like here, it says that what type of shoring was used in the second case study. So as it is in the same context, that's what I was asking here.
Oh, okay, I got you. So, yeah, so for one Vanderbilt, the system there, and actually maybe I'll go back. So the good thing is we didn't really have real earth pressures to deal with on 3 sides of the site.
Okay.
So here, yeah. So when we got, so I'll start with 42nd Street. So 42nd Street, this is where we're going below the subway.
So I think you may want to share the screen.
Oh.
Yeah. Yeah.
Yeah, so 42nd Street, we have a subway structure that will be exposed. We did have to put up some pretty elaborate bracing against the subway structure. And frankly, that's just because of the nature of the conservatism of that agency. There's really no earth pressure there, but we put some bracing there, some internal bracing, so rakers, some diagonal steel rakers that come back to the central mat foundation. And then below that, there's rock bolting and rock stabilization anchors that would be installed below the subway box. On Madison Avenue, this area was very interesting because this is the only area of the site we had earth pressures to really resist. So here we came up with a solution. We had these building vaults, which is a section of the building, the basement that extends past the property line. So we actually filled in that vault with this low strength concrete, this CLSM material, and that material was used to create basically a block retaining wall within that vault space. And then below that, there was a series of concrete piers that extend down to rock. So we created this sort of concrete wall in place before the excavation happened, and then exposed that wall as we excavated. And you can see some of the diagonal bracing that's going in here as we excavate and get down into to a point where we need to brace the wall. But overall, it's rock stabilization around the perimeter with some limited internal bracing at some of the more sensitive areas.
Okay, that's great. And it's very, very rigorous, very interesting. Now, next we have a very long question. I think what I understood is this question is whether there is any grouting done for your KLCC tower for the cavity of the limestone you were mentioning. The question is like it seems there are cavity grouting done for the twin towers, but whether the similar cavity grouting has been done for this KLCC tower N.
Sure. So the boreholes were grouted, and again we drilled a borehole at every single pile location up to 10 meters below the pile tips. So each of those boreholes was grouted. It was not a dedicated grouting program, but it was essentially a grouting of the boreholes, and there was criteria to achieve either require back pressure on the grout to confirm that the grout had extended into if there were any cavities or fractures in the rock, or a certain volume. So yeah, there was some grouting done. We sort of skipped over that here, but it was through the investigation process.
Okay, good. Secondly, in the next question is in Kuala Lumpur Tower, you verified the load of each pile in the design stage in order to define the diameters, lengths, and numbers. Did you have to modify the raft thickness or have a raft with variable thickness depending on the stress distribution?
Right. So that was another thing that we worked with the structural engineer for the project, Lyra Consulting Engineers. They were obviously a very critical part of that whole analysis. And so, you know, we, on our side, we're working in Plaxis 3D. On their side, they're working in SAFE and ETABS. And we get those three models to sort of marry up so that, you know, on their side, they can evaluate structurally what's required. And on our side, we're evaluating what's required from the pile standpoint. So yes, that was part of the overall process, is checking what's the required raft thickness and how does that affect the overall performance.
Okay. So next one, I think you already have mentioned in the presentation that you must have the piles embedded to varying depths because of variable rock depths being met, right? That's what you have shown in your presentation.
Correct, yeah.
So, yeah. So we go to the next one. In Kuala Lumpur, you must have had piles. Okay, same question. Next. Yeah, in Vanderbilt Tower, anchors are close together and individual areas overlap. How was this accommodated in the design and pull-out tests on the individual anchors? Were anchor groups tested for group capacity? I mean, the question is whether it is the group or the individual anchor behavior.
Right. So we did not perform any group tests of the anchors, but we did. So the way we approached this in New York City is we're testing the tensile capacity of the rock on retrieved rock core samples. And from that, there are correlations out there with the overall allowable tensile capacity of the rock. So we're taking that and then we're going into essentially, you know, 3D modeling of what this overall rock cone would look like. And then you can vary the sort of apex angle of the rock cones, and you can look at, you know, if it's 30 degrees from vertical or 45, how does that affect the overall kind of volume of the rock itself that's being engaged, plus the peripheral area that's being engaged in tension. And then we'll look at, you know, maintaining a minimum factor of safety there on this overall global pullout. Is that clear?
Yeah, yeah, I think it's very clear. In fact, I remember you have shown a diagram also where there is an overlapping of the stress, overlapping of the zone. Yeah, I think that's what.
Correct. Yeah, I mean, this is
correct. This is the one.
Very diagrammatically, but ultimately we would take the actual layout and put that into a 3D model to see what is the total volume of that cone. You know, all these cones kind of merge together, and what is the peripheral area that's going to be engaged. And then if you have a tensile capacity along that rock interface, what sort of uplift capacity does that cone provide?
Yeah. Okay, let's move on. Okay, next question is whether anchors double corrosion protected?
That's correct, yes.
Okay. So next question is, with increasing use of pile foundations and development of taller and high density skylines in cities next to a water body, isn't there is a possibility of all these piles acting as a single group and causing group action of pile for the entire city block, thus increasing the rate of consolidation and ultimate settlements? How to mitigate such challenges? I don't know. What's your comment on this, Seth?
That's a tough one. I'm trying to find what that is to see the exact wording again.
Well, I'm not sure how it can increase the rate of consolidation anyway.
So the good thing is that at one Vanderbilt, we're very far inland from the water. That's one thing. And KL as well, there's a high groundwater condition there, but we're not near a body of water. But yeah, I guess I would say that the analysis that we performed accounts for the overall pile, group, and soil structure interaction. I think that's all I can say to that one.
Yeah, the next question is interesting that I also wanted to check with you. What is the load sharing between the raft and the pile in KLCC case? Because your piles are too long, I mean, very, very long. So, and how much percentage roughly of the load been shared by raft and the piles?
Yeah, so about 80% of the load goes to the piles.
Okay.
Yeah.
Okay. Okay, so 80%, 20%. Okay.
Yeah.
So shoring question we already answered. Then next one is, for Tower M, did you consider any soil discount or liquefaction consideration? For one, I might have missed, but what was the criteria to consider anchors into one area if you are having vice versa movement? Did you consider reduction of frustum area for pull-out capacity and test per PTI as per PTI and FHWA? What was lockdown load, test load, was that varying? It's many questions together, I guess.
That's fine, yeah. So for Tower M, we did not account for soil liquefaction. We did do some very early on. We did some site-specific seismic analyses for this area, and liquefaction was deemed not to be an issue. The Kenny Hill soil is a very stiff soil, and there's a fairly low seismic hazard in this region, so that was deemed to not be an issue. And then for one Vanderbilt, the anchors, so that this was all coming from a wind tunnel test. So RWDI ran a wind tunnel model, and so the area that was identified as having an uplift issue was through that test. And then yes, we considered the reduction. I think what you're getting at there with the frustum area is what we were just talking about with this global kind of cone that's created with the group of anchors, and just how we analyze that. So again, we created a 3D model of the actual anchor configuration, and looked at, you know, sensitivity on what this frustum kind of geometry was, and the volumes and overall capacity associated with those volumes are. Lockdown load and test load. So all the anchors were tested to the same load. We would test each anchor to 1.33 times its design load. So the anchors were 350 kip anchors. I'll get you a conversion quickly on what that is in kilonewtons. So it's about 1,500 kilonewtons.
Okay.
And then the lock-off load, yeah. So we would lock these off we generally lock these off between, say, 50 and 100% of the design load. In this case, I believe they were locked off at 80%. Honestly, I don't remember the exact lock-off load at this point, but yes, they are all locked off. So they're a post-tension element to prevent any sort of elongation in the anchor, or limit the elongation in the anchor.
Okay, great. I think then the next question is how the vibrations were controlled in NOIC project, as it is the middle of the important building. Yeah. Yeah.
So we had a very a robust monitoring program that goes along with these types of projects. So really all of the adjacent subway structures, the adjacent Grand Central structure, those have remote seismographs that are mounted throughout those structures. And those are all linked to a common alert system. So if there is an area where when they're chopping rock, they start to get to a high vibration level, we'll get an automated alert via email, via text message that tells the team that they need to back off or use smaller equipment. So yeah, there is an automated vibration monitoring system, and then there's also optical monitoring that goes along with that to identify any potential displacements of adjacent structures.
Okay. Shoring you have already addressed. Did you use partnering with various entities of the project?
So I guess I'll just speak for Langan. So for One Vanderbilt, we did end up working, we originally were working for the developer, and through the construction award process, when they brought on a foundation contractor, the foundation contractor had some ideas on how to modify the shoring system. And so we worked with them to get to a point where those shoring approaches could be implemented. So working with the agencies to go back and get those approved. And so, yeah, I would say that was a partnering process and actually very helpful for the project. We came up with some very streamlined approaches, especially on that Madison Avenue side.
Okay. So next question is, was there a baseline report you faced to deal with variations in quantities and timelines?
So a baseline report, meaning, I guess, is that, I'm wondering if that's related to the monitoring.
Yeah, most likely.
The monitoring, yes, there was baseline vibrations and optical readings taken. It's a baseline related to potentially the KL Tower M, that there was a initial estimated pile length that was ultimately then refined through the construction phase proof drilling. So that, I hope that answers the question. And then in terms of challenges we face with varying quantities and timelines, yeah, I mean, especially with KL Tower M, some of those piles, even through proof drilling and everything, with this updated rock profile and estimated pile lengths being refined throughout that process, there were still surprises when we get out there and start drilling with the, you're drilling a small diameter borehole versus a 2.5 meter diameter borehole with the piles. So there were still some challenges there that we had to just work with. We had a person on site full time. The engineer of record, the local engineer of record, also had representatives on site. So as those challenges came up, the engineers on site with the contractors would work through those issues.
Okay. Then I think we can quickly take one question before we conclude. Was there any post-construction monitoring in both the sites? How was the variation between the observed and computed values of load sharing by piles?
So the tower is not built yet, and so that's something that we'll have to, I guess we'll have to have an update, future date on that. Hopefully next 10 years or so.
Yeah. Now we just take final one. Was there any dewatering in NOIC project?
Very minimal. The rock in New York City is very, very tight, at least in this area, and so there was very minimal water to deal with beyond just incidental rainwater, some leaking utilities, that sort of thing around the site, but no global dewatering system, thankfully.
Okay, I think that pretty much sums up the questions. Excellent, Mr. Martin. I mean, you have patiently, adequately addressed all the concerns raised by the audience. I thank you for your time for that. On behalf of DFI, it's really a pleasure to have you today in the evening, and it's a fantastic lecture for today.
Everybody.
What we have here, today we have couple of excellent demonstrations of challenging foundation construction. I mean, both the cases, the challenges are there in a different level. In one case, you have seen that the piles are, I mean, the huge piles, and it's going up to a very, very deep into the ground. And there is a variable rock strata, so you have to really optimize the length of the piles. And on top of that, you have an adjacent MRT line. So everybody in here can understand, can appreciate the challenge. The other one is other side of the story. In New York, you are doing right in the heart of the city, right at across the Madison Avenue. I can imagine how much traffic, how much I mean, hustle and bustle of the city will be there, and in midst of that, you will be doing such an certain rigorous foundation work with such a tower construction. It's a monumental work, and we thank Mr. Martin again for enlightening us with these two classic examples of modern constructions where we know all the scientific and the mechanical tools, but now we have to deal with the real urban environment and how to counter, how to go ahead without much disturbance to the existing urban system. And that is the challenge for the future. And that is kind of reflected in today's session. Thank you, Mr. Martin. Thank you, DFI, for this excellent session.
Thank you.
It's over to you, Ashrita.
Yes, thank you. Thank you, Professor Subhadeep Banerjee, for your coordination. And also we thank Mr. Seth Martin for the informative session. Thank you all. Thank you for the cooperation. DFI 2022 upcoming webinars. DFI India is conducting a special webinar next week on 22nd March from 5 to 6 p.m. IST by Dr. R.P. Singh, Deputy General Manager, NHSRL, on live virtual tour to Asia's biggest geotechnical laboratory, which is the laboratory set up in Surat for Mumbai-Ahmedabad high-speed railway project. And webinar 4 will be conducted on 19th April 2022. And the title and the speaker details will be shared soon. Thank you all. Thank you for attending. See you on the coming webinars. This is Ashrita signing off.